All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. All right, so we're just continuing right along today. And so on last time we met on Thursday, we talked about elimination methods, which is kind of our first batch of nonlinear programming optimization algorithms. We're continuing with that today. And today we're going over a class of methods that I call interpolation methods. So we'll go over what that means and how to execute one of those. And so I have another example for that. And for this one, I also have a code that we can go over together as well. Okay. This will probably be the most lengthy algorithm that we've done so far. By comparison, the elimination methods were kind of fairly straightforward, at least in terms of the number of steps. So you'll see this one is a bit more complex. And even the sample code that I have for you for interpolation method is, I believe it was like 120 lines long. So there was quite a lot to go over. So whatever we don't finish today, I think we'll just finish up on Thursday. Okay. All right. So other announcements. I have your exams again today, and so if you didn't get a chance to pick it up last Thursday, you can pick it up today. I'll bring them again on this Thursday, but then after that, I'll probably stop bringing them to class. And so if you don't pick them up after this Thursday, you can come to my office and pick them up. Okay. All right, and the other announcement, remember homework 4 is posted online right now, and so it is quite a lengthy homework when you combine both kind of the hand calculations part and the map part. So make sure you start it early because there's kind of a lot to do. Okay. All right, any questions I can answer before we get started for today? Okay. All right, so let's go ahead and continue along. And so the subject for today is interpolation methods. Okay. So interpolation methods, they belong to the same class of methods that we started the last couple of weeks, right? So remember, everything that we've been doing so far has to go under the category of nonlinear programming. Okay. Okay. So nonlinear programming, or NLP, is the broad class of methods, or kind of the introduction to modern methods of optimization. Okay, and so all of these methods have kind of the same thing in common, in that they try to separate themselves from the classical methods. Right. So remember, in the classical methods, um, in order to find the optimum, we had to take derivatives of the objective function. Right. Right. So we took derivatives, we set them equal to 0. Sometimes we took second derivatives just to determine whether you have a max or min. Okay. But nonlinear programming aims to kind of break this crutch. Okay. So the whole idea with nonlinear programming is to say that, can we find the optimum of a function, of an objective function, without taking its derivative? Okay. So in that sense, it's kind of opposite from the classical, right? So all we're relying on in this case is not the objective function derivatives, but objective function evaluations. Okay. And all an objective function evaluation is that we just take our objective function and we evaluate it, or we plug in a certain value of x, and then we just get the result. Okay. So that's the whole idea with nonlinear programming, is to, just rely on the function evaluations to obtain the optimum, right? So we've kind of already seen the extreme of this. And so kind of the extreme of this is to do something called exhaustive search. So remember, that was the first algorithm that we went over. And exhaustive search, all it did was just evaluate the objective function at every single possible point within a range, and just whatever we found to be the optimum from those, thousands or millions or billions of evaluations, that's our optimum. So that is effective, but it's not very efficient, right? And so usually you want to be able to find your optimum, without having to evaluate your objective function, millions of times, right? So, our goal with these algorithms is to try to see, can we do a better job than exhaustive search, right? Can we find an optimum in the least amount of function evaluations? Okay. All right, so that's what our all of our algorithms aim to do, is to basically choose where we evaluate our function a little bit more intelligently or strategically, so that we can obtain the optimum in the least amount of tries possible. Okay. Okay. So we now enter interpolation methods. And so, I've kind of spent the last 5 minutes, building up this idea of, nonlinear programming. We're not going to take derivatives. Well, interpolation methods, we kind of cheat a little bit. Okay. So the whole idea with interpolation methods is say that, we can't take the derivative of the objective function itself, but what if we approximate that objective function with another function? Okay. Because if we can generate a second function, and oftentimes we call this the surrogate function. Okay. So if we approximate our original objective function with the surrogate function, where, we can have control over, what exactly the functional form of that surrogate is, then we can take derivatives of this surrogate function. Okay. So that seems kind of cheating, and also it kind of seems kind of backwards in terms of, what all the problems that we've been doing, right? So because of all the problems we've been doing, our objective function, we can evaluate it pretty easily. And so, taking that objective function and approximating it with the second function, and then taking derivatives of the second function, kind of seems like a very roundabout way of doing these things. But, there's kind of a very good reason for this. Okay. Right. And so just to remind you, sometimes, our optimization problem is kind of formed in such a way that you're not able to take derivatives of it with respect to the design variables. Okay. Okay. Remember the example that we talked about last time where, maybe you're trying to optimize something within a finite element simulation, right? And so in that case, your objective function is probably going to be based on your finite element result, okay? And your finite element result is not contained the design variables, okay? So the whole appeal of using a surrogate function is that we can control, exactly what goes into our surrogate function. And so we can basically control our surrogate function to explicitly contain our design variables, okay? And if we can control that, then we can solve it in kind of a normal classical way, okay? So let me give you a kind of a visual example of this, okay? So let's say that we're designing the dimensions of a building, right? So let's say that we have a building here, right? So let's say one of the dimensions that we are optimizing is the height of the building, okay? All right. So our objective function in this case is to make sure, so let's say that we're mostly concerned with the structural integrity of the building itself, okay? And so what we can do, or what's commonly done, is that you can run a finite element simulation on this. And so you can basically apply modes to this building and predict, what are the stresses and deformations going to be. Okay. So you can do that in SolidWorks, you can do that in ANSYS, for those of you in 410 as well. Okay. And what you can obtain from this is, maybe you obtain some kind of factor of safety. Okay. And so the goal of our optimization might be, let's maximize the factor of safety of this building, right? So let's say our objective function, which is a function of h, the height of the building, is going to be our factor of safety, okay? All right. The problem with this is that, the way we compute factor of safety is not just a simple function where we can plug in h, right? It's a little bit of an indirect way of computing factor of safety, right? So the way we compute factor of safety is that we specify an h in step 1, right? We run the finite element simulation, and then from the finite element simulation, we compute factor of safety, okay? But because of this objective function has no explicit dependence on the height of the building itself, right? In other words, h does not show up in this objective function, right? The objective function is just an output from the simulation. Okay. So this right here is kind of a classical example of why you need nonlinear programming, because your objective function here, is computed through kind of a more roundabout way. Okay. So if we wanted to solve this problem using interpolation methods, what we can do is we can form a surrogate function. Okay. So our surrogate function is going to be an approximation of our objective function. Okay. So we'll call this f with the squiggly hat. Okay. So f with the squiggly hat, which is a function of h. And let's say that we define it to be a simple quadratic equation. Okay. So we said a plus b times h plus ch squared. Okay. Where, we're going to spend most of today talking about, how do you determine this a, b, and c. Okay. That's still kind of a mystery. But let's say that we're able to obtain those coefficients. Okay. What we can do, since our surrogate function here is a simple quadratic and it explicitly depends on our design variable h, we can take its derivative. Okay. Because from there, we just have a simple quadratic function. So we've optimized, dozens of these in the past, in this semester so far. Okay. And from that, we obtain the optimal solution for H, which we can plug back into our design. Okay. All right, so that's kind of the idea is to take a situation where you're in a situation where you can only evaluate the objective function. You're going to create this kind of made up surrogate function so that you can take its derivative and then use that to obtain your optimum. Okay, that's kind of the idea of the interpolation. But of course, the most difficult part is going to be down here. Okay. So how do we obtain the surrogate function, and how do we make sure that it's a good approximation of our original objective function? That's the main challenge of interpolation. Okay. All right. Any questions on kind of the motivation for the interpolation methods here? Okay. All right. So how do we obtain a surrogate function? Okay. So anytime you do any kind of functional approximation, it kind of goes in two steps. And so the first step to determine when you're determining a surrogate function is you need to decide what form your surrogate function is going to take. Okay. You need to decide whether you're going to have a linear function, a quadratic function, a cubic function, a sinusoidal function, an exponential decay function, exponential growth function, right? You need to decide kind of what form that you need to take before. Okay. And you guys probably have some experience with this as well. And so if you've ever taken a data set on like Excel or Google Sheets, probably one thing that you've added at some point is a trend line for those data points. And so a trend line is nothing more than just a linear surrogate function. So you're taking your data points and you're trying to fit it to a linear function. Okay. So this whole idea of a surrogate function is that idea kind of just expanded into that. Okay. So what's an appropriate functional form for an optimization problem? Well, for an optimization problem, we need to make sure that our surrogate function has a clearly defined optimum. Okay. So it needs to have a form in order to do that. And so the simplest function that can do this is a quadratic function. Okay. So a quadratic function, if you kind of plot it, a quadratic function is kind of characterized by its very clearly defined parabola. And that parabola always comes down to a min or a max, depending on if the parabola is concave up or concave down. Okay. Okay. I'm just going to say minima for now, just because we're gonna work under the assumption that we're finding minima here, but a parabola can also reach a max if you're okay. Okay, so that's step one. And in fact, we've kind of already made that decision in terms of what type of function that we're going to use. Okay. The second thing you have to determine is after you have the form is to determine the coefficients or compute the coefficients of your surrogate function form. Okay. So after you determine the form, the next step is to write out the most generic form of that function. Okay. So if we take a generic quadratic polynomial, We have f of x. So a quadratic polynomial has three terms. And so, not only do you have to include the highest order polynomial term, which in this case is going to be x squared, you have to include all the lower order terms as well. So we have to include the constant term, which is typically a, plus the linear term. So the linear term is just some constant coefficient multiplied by x, plus the quadratic term itself, plus cx squared. Okay. And so when I say that we have to determine the coefficients, what I mean is to choose the values for A, B, and C, okay? So we need to choose the values for these coefficients, okay? And how are we going to choose these values? Well, we want to make sure that our surrogate function approximates our original function as closely as possible. Okay. So our surrogate is of no use to us if it doesn't approximate our original function closely. Question, yes?
Isn't the value of A irrelevant if we're going to take the derivative?
It is. So in our case, it is. And so this is just general surrogate functions in general. We will use it. So it is part of forming our surrogate function, but in terms of just taking the derivatives, A does go away. Yeah, good point. Okay. So how do we do that? So how do we choose these to make sure it matches our original? So I think the best way to illustrate this is with an example. But just to sum it up in a nutshell, we have three coefficients to choose here. And so the best way for us to choose their values is to evaluate our original function at three different locations and use that to compute these values. Okay. Okay. So let's do an example to kind of see how this all works out. Okay. So let's form a surrogate function, a quadratic surrogate function. Okay. And we're going to do that for the following function. So we have our original function here, f of x, is going to be equal to x to the 6th power minus 9x cubed plus 2x squared minus 11. Okay. All right. So we have a 6th order function here, excuse me, and we want to approximate this with a surrogate function that's quadratic. Okay. And so the surrogate function that we want to form, so we'll say it's f tilde of x is equal to a plus bx plus cx squared. Okay. So we want to choose the best values for a, b, and c so that our surrogate function matches our original function as closely as possible. Now, granted, it's going to be impossible to fully approximate it or to have it match but a one-to-one, just because it's fundamentally a different function here. But we want to get it to be as close as possible. Okay. And so just like the tooltip above there says, so the way that we're going to do this is we're going to evaluate our original function at three different locations. And from that, we're going to form a system of three equations to solve for A, B, and C. Okay. And the three locations that we're going to choose here are going to be x is equal to 0, x is equal to 1, and x is equal to 2. Okay. Okay. So let's form these three evaluations here. So we have f. This is original f. This is not surrogate f. Okay. So we have f of 0. And so we're going to take our original function here and plug in 0 for everywhere that we see x. We have 0 raised to the 6th power minus 9 times 0 cubed plus 2 times 0 squared minus 11. Okay. All right, and so if we evaluate this with just everything with x just goes away because it's 0, we end up with minus 11. Okay. Now let's do the same thing at x is equal to 1. So we have f of 1 is equal to 1 raised to the 6th power minus 9 times 1 cubed plus 2 times 1 squared minus 11. Okay. All right. This one also is pretty straightforward to evaluate. 1 raised to any power is just going to be 1. So we said 1 minus 9 plus 2 minus 11. That gives us a minus 17. Okay. Okay, and then we're going to evaluate this at x is equal to 2. So we have 2 raised to the 6th power minus 9 times 2 cubed plus 2 times 2 squared minus 11. Okay. All right, this one's a little bit harder to evaluate here, but through the magic of me doing this example last year, I already know the answer to this. This is minus 11 as well. Okay. Yeah. There is that. There is a good reason for that, but we'll get to in a second. Yeah. Yeah. How you choose the gap there is actually very important. That's a good observation. Okay. So what we can also do now is that now that we have these three function evaluations, we can also evaluate our surrogate function at these three locations as well. Now, we won't be able to get a number from these because we don't know what A, B, and C are, but we are going to be able to get functions for A, B, and C, okay? So the idea is to get a linear system of three equations for our three unknowns, except our three unknowns in this case are our coefficients A, B, and C, okay? Okay, so let's evaluate the surrogate at x equal to 0 on the first line. If A plus B times 0 squared, or excuse me, B times 0 plus C times 0 squared, okay? At x equal to 1, we have A plus B times 1 plus C times 1 squared. And then for the last one, we have A plus B times 2 plus C times 2 squared. Okay. All right, and so if we take this this system right here, okay, this now becomes a system of three equations which we can solve for our three unknowns. Okay. So I'm not going to bore you with the linear algebra in this case. And so, this is something that, eventually we're going to get a computer to do it for us anyway. So I'll just give you the answer here. All right. So from this system of equations, you would get A is equal to minus 11. B is equal to minus 12. And then C is equal to 6. And so therefore, if we plug these back into our surrogate function, we have f tilde of x is equal to minus 11 minus 12x plus 6x squared. Okay, so just for fun, we can plot these. And so if we plot these two, I mean, ideally, these two functions here should look similar. So the original function and our surrogate. Okay. All right, so let me plot the original function first. Do that in black here. Okay. So our original function looks a little something like this. So there's kind of a flat region, and then it dips down, and then it comes sharply up like that. Okay. This is 1, x is equal to 0, and x is equal to 2. Okay. All right, and then so what does our surrogate function look like? So our surrogate function is a pretty standard parabola. And so it looks something like this. Okay. So not the best fit, right? And so it's not the prettiest thing there. And that's part of the reason is because we're trying to use a quadratic function to represent the sixth order polynomial. Okay. Okay, but this graph here has actually one very important quality that we want, and it kind of goes back to the question of why did we choose x equal to 0, 1, and 2. Okay. And so if you look at this graph, these two functions are pretty, not that similar, but there is something really important that happens in this graph for both of these functions. So both of these functions achieve a minimum, a local minimum within that range. Okay? So between x is equal to 0, which was our kind of our leftmost point, and x is equal to 2, which is our rightmost point, both functions achieve a minimum. They're not, they're different. They're different than each other. So you can kind of make the argument that our surrogate function has a minimum around x is equal to 1. That's kind of the the trough of the parabola, whereas our original function is slightly past that, so maybe like a 1.2, 1.2. But the fact that both reach a minimum there is actually a really important thing. Okay? Right? Because when you form surrogate functions in this way, where you do it based on function evaluations, your surrogate is only going to be really accurate between the points where you choose to evaluate the function. And so we want to choose our window here. We want to choose our function evaluations a little bit, strategically to make sure that the minimum of our original function occurs within that range. Okay. So this is kind of the first step in the interpolation optimization algorithm, is to make sure that your step length, or basically, the places where you're evaluating the original function are sufficient enough so that you can capture the minimum, but not so large that, you get an inaccurate serve. Okay. So step one of the interpolation algorithm is to find out the optimal step size. All right, so we'll go over kind of the logic behind doing that right after this. But are there any questions on kind of how we got to this point here? Okay. All right. So how do we do this? So just to kind of make our discussion here a little bit more general. So in the previous example, we evaluated the function at x equals 0, x is equal to 1, and x is equal to 2. Okay. So if we kind of generalize this, okay. Remember, because we have a quadratic surrogate function, we have to do at least 3 function evaluations. Or actually, we can only do 3. And so we have to do, to choose 3 locations here. So our 3 locations are going to be x is equal to 0. Okay. We're going to kind of make the assumption that x equals 0 is always going to be part of our domain. Maybe not later in the algorithm, but it needs to start. Okay. So our first function evaluation is going to be at the origin. Second function evaluation is going to be at the location x is equal to t, okay? Where t here is the step size. Okay? So for the previous example, our step size was just 1, right? So we evaluated at x equal to 0 and 1. Okay? And then our third location is just going to be 2 times t. Okay? Okay. So how do we choose the t for a given objective function? So, let's kind of take ourselves away from the previous example, and let's imagine that, we're taking a generic just objective function, right? How do we choose that t so that our minimum or maximum occurs within this range? Okay. Okay. So that's the objective of the first part of this algorithm. Okay. Okay. So how do we know this? Well, we have to kind of rely on some assumptions. These assumptions are not as strict as the elimination method. So remember, for elimination methods, we assumed that we had a unimodal function. We don't have to assume that here, but there is, we do have to assume that our function is fairly smooth, and that it does actually attain a minimum in a fairly smooth way. Okay. Okay. And so to kind of illustrate this, I'm going to go over some test cases here. Okay. And to basically tell you kind of what happens if you choose a step size that's too small, a step size that's too large, and what you can do, to alleviate that process. Okay. So for all of these, test cases, you have to perform some function evaluations, and so there's kind of no way around it. Okay. Okay. So for case number one, case number one said if you evaluate your objective function at the midpoint, and so if you take f of t, okay, and if that's greater than the function evaluation at the origin, right? And so right away, going from the origin to the halfway mark, you see an increase in the function value. Okay. Right. Then the assumption that we make here is that that your equation here or your original function achieved a minimum and then it's coming back up. Okay. Okay. So the minimum has already been reached between 0 and x is equal to t. Okay. And so it looks, it visually it looks kind of something like this. So if we have our original function here, so let's say our original function looks something like this. Okay. We have f of 0. And if we have f of t that's somewhere up here, right? Then kind of the assumption is that, if we already see a function increase, then our minimum was already somewhere in between f of 0 and f of t. Okay. Okay. So we can make this assumption, remember, because we are forming a quadratic interpolation. So the assumption is that our function here, at least our surrogate function, is gonna exhibit quadratic decay. Okay. So this isn't the worst thing, and so at the very least, in this case, we can kind of reasonably assume that we're capturing the minima. But in this case, we're kind of in the ballpark where our function evaluation at 2t is like kind of wasted, because all the actions occurring between x equal to 0 and x equal to t. Okay. And so this is a case where our step size is too big. Okay. And so in this case, you want to reduce your step size, and kind of a good way to do this is to cut the step size in half. Okay. 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 And so after you cut the step size in half, you're going to reevaluate your surrogate function. So you're going to reevaluate the values for a, b, and c. Okay. and then you're going to check your step size again. So at this point, we're not locating the minima itself. We're just making sure that the window in terms of where we're looking is adequate. Okay. All right. Any questions on this? Okay, good. Okay, so that's what happens when the step size is too big. Right. Let's see what it looks like when our step size is just right. Okay. So if f of t, so that's the function evaluation at the midpoint of our domain, if that's less than f of 0, okay, so our function value actually goes down at the midpoint. Okay, and f of 2t is greater than f of t. Okay, so by the time we reach the end of the domain, the function kind of comes back up. Okay. Then what we say in this case is that our surrogate is just right. So this tells us that, within our domain, we're able to observe our objective function go down in value, and then we're also able to see our objective function go back up in value. And so that tells us that, somewhere in between those, then, our function achieves a minimum and, it comes back up. And so, we say that our function, our surrogate function is just right in this case. Okay. Okay, so kind of drawing the figure from above. Okay. So let's say our function looks like this. So we have f of 0 here. Let's say f of t, it doesn't exactly have to be at the minima. Okay, so let's say f of t is right there. And then f of 2t like that. Okay. And so if we were to approximate this with a quadratic function between 0 and 2t, kind of the assumption there is that we're going to get pretty close to the original function. Okay. So that's the best case scenario. So the best case scenario is that your function goes down at the midpoint and then comes back up at the end. So in this case, you don't need to adjust the step size, and then you kind of go into the next step of the algorithm. Okay. Case 3. So we've already seen what it looks like when our step size is too big. We've seen when our step size is just right. What if our step size is too small? How do we know that? Okay. If f of t, so f at the midpoint is less than f of 0, okay, and f of 2t is less than f of t, okay, right? So our function just continuously goes down, right? So in this case, f of 0 is our highest point, okay? Then in this case, it's most likely that our step size is too small, and that we're only kind of capturing just the descending portion of that function. So visually, it looks like this. So we have our function that looks like this, okay? But if our step size is too small, we have f of 0 here, let's say f of t here, and then f2t there, okay? Right. This is kind of the worst situation because you have no idea where the optimum is. So it's not that you haven't even passed over it, okay? And so in order to make sure our surrogate function captures the minima, we need to make our step size bigger. All right, so basically the first step of the interpolation algorithm is to adjust your step size. And so you're going to evaluate, you're going to start with some assumption. And so you have to start with some step size. That's your initial step size. Okay. And then you're going to adjust it until you get the right step size. Okay. All right, so first step in the interpolation algorithm, just your step size. All right, any questions on this? Okay. All right. So after you adjusted your step size, you can of course compute your coefficients. Okay. And in fact, just to kind of save you the effort, we have formulas that you can use to compute A, B, and C. Okay. Okay. So A here is going to be, just like our previous example, A is just going to be simply the function evaluation at x is equal to 0. Okay. B is going to be 4 times f of t minus 3 times f of 0 minus f of 2t, all divided by 2t. So this is basically the solution to our original kind of system of 3 equations, 3 unknowns from our previous example. I just kind of did the algebra for you just so you can have something to plug. Okay. And then our value for C for C is f of 2t plus f of 0 minus 2f of t, all divided by 2t squared. Okay. So once you have the right step size, you can compute these three coefficients. Okay. And then from here, our f tilde is just simply going to be a plus bx plus cx squared. Okay. Now we just have a simple quadratic function here, and so we can take the derivative of this function and set it equal to 0 to find the optimum. Okay. We have d f tilde dx. Okay. We're going to take the derivative of this, and of course a kind of goes away. So a, as I mentioned before, is kind of a little bit of a waste, but we're going to use it again in a second. But we take the derivative, we get b plus 2cx min in this case, okay? Because we're going to set this equal to 0 and solve for x min. Okay. And so we solve this equation for x min, we get minus b over 2c. All right. So far, what we've done in our optimization algorithm is that we've computed a surrogate function. We've adjusted the step size so that the minimum of the surrogate function is in the same realm as the minimum of the original function. Okay, and we computed the minimum from here. Right. So we're done. Right. So we have our minimum here. So that should be it. Right. Of course, the way I say that, hopefully kind of implies that we're not done yet. Okay, so even though we have a minimum here, and I'll call it a guess for now. Okay. But the question is it good? Okay. So we know for sure that the minimum of the original objective function is within our domain, right? So between 0 and 2t. But there's still a lot of latitude, or there's still a lot of kind of leeway in between there. Okay. And so the question we have to ask that is this a good approximation for the actual minima of our original function? Okay. All right, so we can check this, of course. And so we're going to check to see if this is true. Okay. So the way we're going to check this is that we're going to compare the value of our original objective function and our surrogate function at this value of x. So we have to do a fourth function evaluation here, okay? So we've already evaluated our original function at x is equal to 0, x is equal to t, and x is equal to 2t, okay? This x min is likely going to be different than t or 2t, and it's going to be different than 0, okay? And so if we take our surrogate function and evaluate it at x min, and then we subtract that from our original function at x min, okay? And then we divide this by our original function at x min. Okay. So we're basically taking a percent difference between the two. Okay. And so just to make things, just make sure the signs match up too, we're going to take absolute value of this. Okay. And so what this is measuring here is basically the percent difference between our surrogate function and our original function evaluated at our approximate min. Okay. So ideally, if our surrogate function is a good approximation of our original function, then these two should be pretty close to each other. Okay. And so to assess whether we are converged or whether our algorithm worked, oops, not 3, backwards 3. There we go. And so what we can say is that if this percent difference is less than some threshold epsilon, okay, so this epsilon here is some accuracy threshold. Okay. If that's true, and our surrogate function is a good approximation of our original function, then we can stop. Okay. okay? If it's not, and most likely the first time that you do this, it's not going to be close, then we need to refine our surrogate. Okay, so that's the second main phase, I would say, of the interpolation algorithm. So interpolation algorithm phase one, determine your step size. Phase two is to refine your surrogate. Okay. And so the question now is, the question, of course, how do we determine what the accuracy threshold is? That's usually something that you specify beforehand. So usually anything like, I think in my example here, we do a threshold of about 5%. Yeah, so something maybe about 5% is usually kind of a good threshold to have. And the lower you make that threshold, the more accurate your story is going to be. But it's also going to cause more function evaluation as well. Okay. So that threshold is something that you can modify based on how much accuracy versus speed do you do. Okay. Any questions on this? Okay. So I think we'll have just enough time to talk about how do we refine the surrogate. And I think we'll probably save the example for next time. Okay. So let's talk about phase two. Okay. Phase two is to refine the surrogate. Okay. Phase one was choose the step size. Phase two, refine the surrogate. Okay. So the main issue at this point is that if your accuracy check did not pass, then even though you have the right bounds, right? So you're checking within the right range, your surrogate function itself is not well calibrated. So the locations where we evaluated the surrogate for are not good representations of the original function. Okay. So all this really means is that we're going to be choosing different locations to evaluate our original function, and that's going to give us different values for A, B, and C. Okay. Of course, the main ones that we're worried about are just B and C. But A is used here for evaluating the evaluation function. Okay. So we already know our range, and so we're already going to be between 0 and 2t. And so it's just kind of changing the function evaluations and kind of rearranging it to choose A, B, and C. Okay. Okay. So just as a reminder, we have three coefficients here. And so the way that we determine those three coefficients is by making three function evaluations. Okay. Okay. So that isn't changed. And so we still need three evaluations to determine A, B, and C. The question is, what are the three best places to evaluate our function? Okay. So far, or I should say in phase one, our three evaluations were at x is equal to 0, x is equal to t, x is equal to 2t. Okay. So those are the main three evaluations that we've done. But at this point in the algorithm, we actually have a fourth location that we've evaluated our original function at. Okay. It was a little bit sneaky, but we did actually evaluate a fourth location already. And we actually just did it. And so if we kind of scroll back up here, okay? And so when we evaluated our accuracy threshold here, okay, as part of computing the accuracy threshold, we had to evaluate our original objective function at x min. We already have f of x min. Okay? Where x min, right? X min is our current best guess for the minimum of our objective function. Okay. So, in this case, we've kind of already done the work to, to evaluate our objective function. And, the thing with, remember, going back to kind of the beginning of class today, the thing with these optimization algorithms is that you want to find the optimum in the least amount of work possible, the least amount of function evaluations. And so if we've already done the work to evaluate this function here, why don't we use this to recalibrate or refine our survey? Okay. Okay. So how are we going to do that, right? So we only have we need three function evaluations, but we have four, right? So it's a little bit of musical chairs. And so someone's going to be left without a chair, and it's going to be kicked off the aisle. Okay. So our four function evaluations at this point are x is equal to 0. Okay, so that's function evaluation 1. Okay. X is equal to t, so that's function evaluation 2. Okay. X is equal to 2t, so that's function evaluation 3. Okay. And x min, which is function evaluation 4. Okay. So we need to choose the three best locations out of these four to refine our surrogate and recompute A, B, and C. Okay. Okay. So of course, there's different cases here, and so this is kind of another case where we have case 1, case 2, case 3, and case 4. Okay. Okay. So let's go over case 1. So case 1, if you'll notice that all of these are kind of written as if statements, and they're implemented in code as if statements as well. Okay? So if x min is greater than t, and f of x min is less than f of t, okay, right? Then in this case, what we do is we kick out location 1. And so our three locations where we're going to evaluate our surrogate are x is equal to t, x is equal to x min, and x is equal to 2t. Okay. Okay. And so when we evaluate our functions here, or we already have these evaluations, we'll call this FA, we'll call this FB, call this one FC. Okay. just because later on, we need to change our formula for computing A, B, and C. And so I'm just relabeling these points here. Okay. Okay. So that's the first case. Second case, if x min is greater than t and f of x min is greater than f of t. Okay. So the difference between case one and case two here is the second condition. Okay. And so in this case, we're going to kick out. We're going to kick out location 3. Okay. And so our 3 locations where we're going to be evaluating our surrogate for is going to be x is equal to 0, x is equal to t, and x is equal to x min. Okay. And so once again, this is going to be FA, FB, FC. Okay. Okay, case 3. Case 3 is, let's say if x min is less than t and f of x min is less than f of t. Okay. And so in this case, we also kick out location 3. And so our 3 locations where we're going to be evaluating our objective function are going to be x is equal to 0. Okay. Now you have to be a little bit careful here. So if you look at the difference between case 2 and case 3, in case 2, x min was greater than the step size. In case 3, x min is less than the step size. And so the second location is going to be x min. And the third location is going to be t. Okay. And so this is going to be FA. This is FB. This is FC. Okay. And then just very quickly, the fourth case here, if x min is less than t and f of x min greater than f of t. Okay. In this case, we're going to kick out location 1. And so the 3 locations we're going to evaluate our objective function here are x min, t, and 2t. Okay. The first of which is going to be become FA. Second one is going to be FB. And third one here is going to be FC. Okay. Okay, let me zoom out just so you can kind of see all of it, because I know I went a little bit fast there. Okay, so those are our 4 conditions for phase 2. Okay. All right, so when we come back on Thursday, I have a full example to kind of show you this whole process. I know, we spent the whole lecture kind of talking about this algorithm. So it was a lot, I know. This is probably the most complex algorithm we've done so far. But I think once you kind of see it in action, you kind of see phase 1, phase 2, I think it'll make a bit more sense. And on Thursday, we'll go over the code for this as well, so you can see it implemented in that. Okay, so thank you guys for coming today. I have your midterms here if you didn't get a chance to pick it up yet, so you can come get it here. Okay. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you on Thursday. Oh, very doable. Oh, yeah, very doable. I had a last one.
I will be once again watching the recording.
Okay.
I'll let you know how South Dakota goes. I'll let you know if I freeze.
Okay. Hopefully not.
Highs of 20 degrees, lows of 30.
Oh, wow, that is very different.
At
than-
night.
That's very different than here.
In the email, I don't know if you, I don't think you've been receiving the emails.
Yeah.
But in the emails that they've been sending out for the convention, it was like, oh yeah, this is like usual temperature for most of our collegiate chapters. It's not ice, it's like it was like, no, exact words. Oh, we got ideal weather ranges of like low 30s and high 60s. And then in little brackets, it was like, unless you're California or Florida.
I'm sure it gets warm in Texas too. I'm sure it's maybe cold for them too. But
I don't know, but I'm taking a wool jacket and a leather jacket with or
that's not good.
I just don't know if I should take a scarf.
Probably.
And I should probably take a beanie.
Yeah, media and super.
Yeah, and sheepskin gloves, so I think I'll be fine.
Hi, Dr. Grant.
Yeah.
So for this method, are we
Oh,
still capable of doing elimination on this? Isn't that kind of what we're doing is we're
Yeah.
combining it because it's gonna be unimodal if we're doing.
Exactly. Well, so our surrogate could be.
That's what I mean. Our
That-
surrogate we can treat as unimodal.
Yeah,
Even if
actually-
the other one is.
So actually, you can't do that. So once you get a good surrogate, you can technically
You
do
could just
elimination.
do an elimination
Yeah.
method on it.
And so that's actually an interesting, usually it's not done for this, but for kind of for the multi-dimensional problems, people actually chain optimization algorithms back to back.
That
Because-
makes sense.
because certain algorithms are
Start
good.
getting like, some can narrow it down and then some
Exactly.
are really good at getting it, not
Exactly.
just, whereas with some it's like, okay, we're in the ballpark and now you can start getting close.
Exactly, yeah, that's
Okay.
exactly it. So some methods are great for getting you close, but then some methods only work when you start close and you really kind of.
That makes sense.
Yeah. But
Okay, cool. That's what I was figuring, because that's kind of what we're doing with cutting it out, like cutting out our regions. Like, okay, we're gonna get rid of this because it doesn't work well.
yeah, yeah.
Okay. Cool. And then was there any? Oh, I did have a question. It was how we apply stuff. I still
Yeah.
haven't gotten any of my like stuff that.
Yeah, we're still working.
Okay, cool. I was just
Yeah, I'm
gonna
sorry,
check.
they're going to convention this weekend, so yeah, probably pretty.
Okay, cool. I was just double checking.
Uh-huh.
But, alright, do you know like when are like meetings or whatnot? Because I haven't gotten any emails about.
We need to make.
Okay.
Yeah, we're still kind of.
No
coming off
worries.
the ground.
I just wanted to double
Yeah.
check that I was. Cool though. I think that's interesting. Cause that makes a lot of sense as like a starting one there. Okay, cool. Thank you, Dr. Chin.
Yeah. Mhm.